Good afternoon. This is Cristian Contescu. I'm a physical chemist. In the last 15-16 years, since I'm at Oak Ridge National Laboratory, I work on activated carbons and now nuclear graphite. And my interest goes towards surface reactivity of carbons. In this context, I studied oxidation of nuclear graphite for gas-cooled reactors. My colleague Nidia Gallego is also a carbon chemist, and we both activate in the American Carbon Society. Another co-author is Jim Kaiser. He is a long worker in molten-salt problems, and he told me yesterday that he joined ORNL while the MSRE project was still going. And then Kristian Myhre is a radiochemist, and he will end this presentation. ORNL is the place where the first graphite reactor was built here, and now it's a part of the National Patrimonium, and immediately after Fermi's reactor. And also is the place where the first molten-salt reactor was built. And at that time, graphite became one important component of both reactors. Why? Because graphite is used as a neutron moderator in contact with the gaseous atmosphere in gas-cooled reactors, in contact with the salt in nuclear reactor, in molten-salt reactors. The problem is graphite is porous, and intrusion of pressurized salts in graphite pores must be avoided or minimized as long as possible in order to avoid problems with the neutronics. So the scientists that work at ORNL during the MSRE project developed a new grade of graphite with a very low salt intrusion, which is the CGB grade used for building the prototype of the first reactor that worked and was used there. How they did that, they used multiple impregnations and of industrial graphite, very high purity, and eventually succeeded in reducing the pore openings down to about 1 micron diameter. Now at ORNL, we built an experimental facility for measuring high pressure salt intrusion, and we have used it for measuring FLiNaK intrusion at 700 degrees C. We have also characterized the volume of open pores in multiple graphite grades and used Mercury Porosimetry intrusion to correlate salt intrusion behavior with porosity distribution in graphite. My colleague Kristian Myhre will present at the end of my talk his results on characterizing salt-exposed graphites. So graphite is a polycrystalline compound which is made by mixing a paste that contains a filler, either coal tar pitch or petroleum coke filler, and a pitch binder. And then this is formed, and then it is calcined, graphitized at extreme temperature, 2800 degrees C, sometimes even higher. And all this process results in a crystalline structure which is very close, based on XRD characterization, with the crystals of pure graphite. However, the density of this material is much lower, 1.7, 1.8 compared to 2.3, because about 20% of graphite, nuclear graphite, is porosity. For chemists, graphite is just carbon, a very pure carbon. But for engineers, there are many varieties of graphites. They differ by the raw materials, method of fabrication, and other properties. We have and characterized a large variety of materials, graphite materials. This includes those that were considered for candidates for in-reactor components of gas-cooled reactors, and which were included in the irradiation campaign of the Department of Energy. These are the AGC campaign here on the top. Other varieties are not purposed yet for being used in nuclear reactors, but we managed to include them because they have properties that may be of interest for MSRE. And we also have the CGB graphite MSRE that was used initially in this project. Because we talk about intrusion of pores, we need to think about the pores which are available to salts. So we need to measure the extent of porosity which is available. Normally, if you want to measure the pore volume, you need the density and the mass. However, the problem is that for graphite, we can define three different densities. One is the apparent density, which is based on physical measurements of the external body. The other is skeletal density, which includes only the solid part in this and excludes the porosity. This is measured by helium pycnometry. Sometimes this is also called helium density. And third is the real density, the crystal density of graphite crystals, 2.24. So for us, in order to evaluate the volume of open pores, we compare the apparent density and the skeletal density. In another comparison, we can determine the volume of closed pores and the total volume of porosity. Why is this important? Because in some situations, we may have fracture of the graphite structure at very high pressures, which would make available to salt the volumes which initially were closed pores. So it is a ASTM guide which was adopted in 2016 and which is in fact a procedure for measuring the effect of impregnation of salts under controlled conditions of temperature and pressure. So according to this guide, the amount intruded salt is compared with either the open pore volume or the closed or the total pore volume. This is really useful in order to check whether or not pressure caused any kind of pore fracturing and damage to the structure. Based on this guide and following its suggestion, we built at ORNL a salt intrusion system, which is an all graphite construction, such that the salts do not have any kind of contact with metals. Salt is included, it's in this reservoir here. So practically, we have a sample holder at the bottom of this reservoir and a long rod which is terminated with a sample holder, and this rod can be either lifted up or lowered down in the molten salts. We conducted experiments with FLiNaK, and the operating range is a maximum 10 bar and temperature of 750 or more. Here we have a few photographs showing the dismantling, disassembling phase. You see the pressure specimen holder here and the long rod. And here you see the all assembly in position in the high temperature furnace, which is hosted in a all glass box, which is flushed with argon with very low water vapor pressure. Actually, it's dry argon and pure. Here you see the sample holder with specimens, and one after immersion in FLiNaK, there is some salt residues on some of the graphites. We use mercury porosimetry to explore the porous structure of various graphites. Mercury porosimetry is based on a very simple principle. You take the specimens machined in this shape like cylinders, and they are placed in this penetrometer, which is sealed, and then it is flooded with mercury, does not wet graphite, and after that it's pressurized from outside. So what happens when we increase the pressure, initially the pores are not filled, and then applying pressure higher and higher, pores become filled, starting with the pores with a larger throat at low pressures and gradually going to pores with very narrow throat at highest pressure. After intrusion, one may attempt a extrusion run, which will eliminate mercury from the pores with a larger and medium throat, but may leave some graphite still in this pores with a very low, very narrow throat. For graphite, sometimes the pressure is so high that the structure of these fragile pores with very narrow throat is destroyed, so that graphite, the mercury becomes trapped in these pores and cannot be removed. So this gives the irreversible part of the mercury intrusion diagrams. The relationship between pore diameters and pressure is in this Washburn equation with two parameters, which one is the surface tension of the liquid mercury, and the second is the contact angle for the interface between mercury and the graphite. We have done several experiments of measuring porosity of about 12 grades of graphite with different structure, pore size, and density and method of forming. And here you have the raw data that show the intruded volume, centimetric cube per gram, versus mercury pressure. The range of this is from very large pores, about hundreds of microns, to very, very narrow pores in the nanometers range. And the pressures go very, very high. This is 100,000 psi. So you see two groups of diagrams here. The fine grain graphite, so it grains smaller than 50 microns, show a very definite, a very clear penetration of mercury in a very small, very narrow pressure range. And then the mercury remains most of all trapped, but in general, they will reach the available volume of open pores that we measured with mercury, with kilometers, excuse me. Now for medium grain graphites, you don't see the same feature. When the volume intruded reaches the volume of open pores, intrusion continues after that and reaches very high limits, and then on the extrusion branch, mercury is really trapped inside. These are clear definitions of structural damage occurring at very high pressure in this type of medium grain grades. And this is the domain of structural damage. Now, with Washburn equation, we can convert the data shown before, not on the scale of mercury pressure, but on the scale of pore size in microns, logarithmic scale here. And here we have the volume of mercury intruded. You see again the difference between fine grains that have this very distinct percolation pressure, and in opposition you see the behavior of medium and large grain graphites that have a very broad range of mercury intrusion. And also you see here the structural damage which creates some kind of false impression of porosity. The same data now are put here on a differential scale just to see the exact location of pore openings for a variety of grades here, and they are listed in this table for diameter here and grain size. And in contrast, you see the behavior of medium grain graphites that show a very broad and unstructured uptake of mercury, and the structural damage, which is not showing very, very fine porosity, but it's showing structural damage. Next slide, we can connect mercury pressure scale with FLiNaK pressure scale using the same Washburn equation, parameters for surface tension and contact angle for mercury, for the salt, and the same parameters for mercury. And by doing this, we use the intrusion measurement for FLiNaK and compare with the with the pressure of molten FLiNaK. The lines here, the continuous lines show the results from mercury porosimetry. So the same volumes are intruded by mercury first, as we show. But we also have in the literature several publications that show experimental data obtained by others. So we could compare these results with our mercury intrusion, and we see pretty good correlation. we need two sets of parameters. For mercury, the surface tension and the contact angle are well defined. For molten salts, there is a report from Idaho National Laboratory that shows this contact angle and the surface tension, but this is limited, and in fact, not all combinations that we saw before on the previous presentation are characterized with these parameters. And moreover, a recent work from Wisconsin University showed that for FLiNaK and graphite, contact angle may vary depending on the roughness of the graphite surface and also depending on the presence of oxygen or moisture in the medium. So we need to be careful, and we need more measurements of these parameters for the exact system that is of interest for us. And here on the same plot, I added our results with the large symbols here. And they show results for impregnation at 6 bar and 8 bar. As you see here, the 6 bar, we have less than 8 bar. One other thing is we have just one single attempt to use a CGB, and we find a very good resistance to intrusion, exactly as the data measured by MSRE show, and in very good agreement with the Mercury porosimetry predictions. So people at MSRE stated that we need to have graphite with pores narrower than 1 micron, and actually only 2 grades that we investigated in our measurements so far, this is CGB and the POCO graphite grade, have these very narrow pores, and we did not measure yet the POCO graphite here. With that, our test will continue with more measurements with FLiNaK in order to add more data points for our model based on Washburn equation. We plan to design and to build a FLiBe dedicated system which will be used for this salt and maybe others, and is hopefully available by next summer. And we also look at characterization of salt-exposed samples to understand chemical interactions and structural changes in graphite. But about this last point, I'll pass now to my colleague, Kristian Myhre.
Nidia and Kristian requested that I speak about the laser induced breakdown spectroscopy measurements that we've been exploring, as well as some additional experiments we're planning for correlative analysis with the LIBS. So briefly, this slide shows what we've been working on this year with the laser induced breakdown spectroscopy of these graphite samples exposed to molten FLiNaK, as Kristian mentioned. So these are, for instance, 6 samples from one of these intrusion measurements that we've then loaded into. In the top middle image, you can see a sample carrier. We've loaded these 6 samples in a glove box with everything kept under inert argon atmosphere, and there's a inlet and outlet where we can change, while maintaining an inert atmosphere, the atmosphere to a helium during the LIBS measurements, which allows us to measure the fluorine. We then get a, for instance, 10 by 10 grid of laser shots on the surface and drill down at each one of those spots, however many depth we wish to go. So for these samples, we were looking at about 200 shots per spot, so 20,000 spectra per sample. Each spectra on the bottom left looks something like that, where you've got carbon, fluorine, lithium, sodium, potassium, oxygen, and hydrogen being the main elements that we were interested in seeing in these samples. And then we take that spectral information with the intensities being related to the concentration. We get something like either a line scan shown in the bottom middle, where that's just a function of depth. What's the ratio of fluorine, potassium, lithium, or sodium to carbon? And so it tells us about the distribution as a function of depth of the FLiNaK constituents. And then we can take and reconstruct that into a 3D map of those constituents. We can also apply and have been looking at advanced data analysis techniques to understand how we can correlate some of the the different behaviors of these elements, see if there's partitioning of the fluorine from the FLiNaK and things like that. So again, everything is kept under an inert atmosphere, so we're also able to measure oxygen and hydrogen in this case. What I showed you was the work we did this FY20, just looking at FLiNaK exposed samples to work out the methodology. We're now working through systematic set of samples that have been exposed in a systematic way to FLiNaK. We're also, this FY21, going to be standing up a second carrier that we now have in hand that will be able to, it will be dedicated for beryllium samples. And eventually we'll also be able to do radioactive samples. We're also looking at, so that's all elemental analysis. We're also looking at molecular analysis to understand and correlate the chemistry to the elemental compositions with FTIR and Raman. And so we'll be working on that. So this is really, I know we're ending now.